Okay, so we are going to start with the inverting amplifier. So this is the configuration of inverting amplifier. You can see that the positive terminal here is connected to ground and the input signal is given to the inverting to the negative terminal. Alright. So what I want you to take note is that just imagine that this is your voltage amplifier block, okay, for the op-amp, right? And similarly, okay, this is just like the one in your chapter 1 here, okay. So you can see this is the voltage amplifier portion. Okay, so this is the output signal, okay, and you can see the input side is connected with your input signal. So RS ni is with your R1 here and VS is with your V1 here. Okay, so it's just a difference in the notation here, but the concept is the same. Okay, so I'm gonna wipe this off. Okay, so if you look at the properties of op-amp, the one that I mentioned in the slides before, we want to use the ideal case, the ideal op-amp for our operational amplifier calculation. So the first one is we want the open loop gain to be equal to infinity, which means that V2 equivalent to V1. So if I want to bring this circuit symbol to overlap with this inverting amplifier configuration, so I'm gonna crop this, just make it more smaller. Okay, so if I overlap this, right, which means that you can see the terminal 2 is here, okay, at this part, alright, and your terminal 1 is here. Okay, so to take care of the first line here, the first characteristic here, we want this node here to be equal to this node, the voltage lah, right? So if I just take this away for a while, okay, so you can see your node 2 here is directly connected to ground, so it's grounded, right? So because it is grounded, okay, so because it is grounded, alright, we can safely say that V2 equivalent to 0 volt, okay, because this node is directly connected to ground. And because V2 is 0 volt and we want to take care of the first property, the first characteristic, this node is also 0 volt. Okay, so node 1 here is also 0. Okay, the first one is done. For the second one, the input resistance to be equal to infinity, hence there is no current going into the op-amp. Okay, so we know that Ri for your op-amp is infinity because it's open circuit here. So I in is actually 0. No current going into your op-amp. Alright, so we just take note on the second line, the second property here, where the current I in is 0. No current going into your op-amp. Okay, so I would like to talk to you about R2, why we have R2 over here. So the reason is because, let me take this away. This is because if there is no R2, just imagine that if there is no R2 in your circuit, so it will look something like this, kan? And if I have a load here, because it's, let's bring this to the front. Okay, so if I have a load here, okay, and I have this input signal, so the current I1 and I in is the same lah, because it's at the same path. But because of this second characteristic, actually no current is supposed to go into your op-amp, kan? Right? So the current cannot flow and basically the circuit is cannot be completed. The circuit is not complete, it's open. So this is still in open loop mode, right? So having R2, so by having R2 in your circuit configuration, you will allow the current to flow through R2 like this. Okay, so I'm going to show you. So the current will flow here. So your I1 will split I2 and this is your 0 current. Okay, so basically I1 and I2 is the same actually. and it goes to your RL and complete the circuit. So this is in your closed loop mode. So that's why R2 is very important. Okay. So we already know that your op-amp is in the closed loop mode. So we want to calculate what is your V out over V1 here, which is the input signal. Okay, and we already established that this is 0 volt because it's grounded. Okay, this is 0 volt because it's grounded, which means that it's also 0 volt. Okay, V1 must equivalent to V2 over here. Okay, so actually to derive this voltage gain, the concept is using KCL. Okay, so basically I1 minus I2 minus I in, right? Okay, so we know that based on the second characteristic, there is no current going into your op-amp, which means that the current here is 0. Okay, so there is no current here, I in. So you are only left with I1 minus I2. Okay, now just to recall back about KCL and how you do nodal analysis. Okay, so if you have a resistor, okay, and the current flows from VA to VB, the equation to calculate your current is I equivalent to the voltage at node A minus voltage at node B over resistor. Okay, the current direction will indicate on which voltage to start first. Okay, so it goes from left to right, so VA minus VB over R1. Okay, so similarly you have this I1 minus I2 kan. Okay, and we already know that this node is 0, so you look at for the branch I1 here. Okay, so this is actually V1 minus 0. Okay, V1 minus 0 over R1. Okay, that's for your I1. And I2, okay, is 0 minus V out over R2. So I already bring I2 over here. So that's why you have the negative sign is gone, because I bring it over here, and I left with this equation. Alright, and because I want to calculate the gain V out over VI, so I bring V in over, and I am left with V out over V in equivalent to minus R2 over R1. Okay, so you have this equation for the voltage gain, okay, for your inverting amplifier. Right? So why do you have the negative sign? Okay, because it's inverting, which means that your output will be inverted. Okay, so if this is your input, then your output, it will be amplified but inverted. Okay, so it is amplified lah, but it is inverted. Right? Okay, so let's go to the next example for inverting. Alright, so you can see here, let me wipe this off. So this is obviously a direct representation of an inverting amplifier. So your non-inverting is grounded, input signal, and your feedback resistor. So you can see that we do not label for you. We do not label that this is R1, this is R2. So you need to know. So if you do not remember, like for example, my answer here, the solution is straightforward because I know this is an inverting amplifier. Okay, let's say you not sure. Okay, so you go back to basic. You go back to basic by remembering the two characteristics, which are this node and this node must have the same voltage, right? Okay, just remember the characteristic. These two must have the same voltage. And the second property is that there is no current going into your op-amp. So the current here is 0. Okay, so that is the two properties for your op-amp. Let's say if I want to do the derivation work. Okay, so if I want to define I1 is here. Okay, and then again I2 is this current and I in is this current. Okay, and we know that this is 0. Okay, so V in, so okay, so VI over here, it's called VI tak apalah. So your VI minus 0. Why is it 0? that I mentioned is because it is grounded kan. Your V2 here is 0 volt, so this is also 0 volt. So V in minus 0 over R1 equivalent to 0 minus V out over R2. So your R1 is 12, okay, and your R2 is 150, okay, 150 kilo ohm. So make sure it is the same group. If it's kilo ohm, then it's okay. If both are kilo ohm, then it's okay. So I have V in over 12. So this is 12, and this is 150. So you are left with 150 over 12, and you get the same answer, minus 12.5. Okay. So if you are stuck and you are not sure, just go back to the derivation mode. But you need to remember the two properties. Okay, otherwise it will be hard for you to move forward. Okay, next is another example, and this is a bit tricky, but actually once you get the hang of it, you will know what to do. So a voltage source with source resistance Rs is connected to the input of an op-amp inverting amplifier circuit. R1 is 1 kilo ohm, R2 is 15 kilo ohm. Calculate the voltage V out over Vs, and calculate the output voltage for the source voltage Vs 45 millivolt. Okay, so in order to make this configuration similar to the op-amp configuration of inverting amplifier, so if I just copy this and paste this here, so what do we need to do with the two resistors that are connected this way? So this is connected in what? So these two resistors are connected in series, right? So if series, what should we do? We should add, okay, the equivalent resistance. We are supposed to add them up. So just add Rs and R1. So you are left with a resistor. Let me call this a resistor R total lah, RT. Okay, so if I add Rs and R1, it's 1 plus 1.5. So RT is, let me just drag this. So RT is equivalent to 2.5 K, right? So it's 2.5 kilo ohm. Okay, and R2 is 15K. So now I have this configuration, and then I convert it into the standard inverting configuration. So you can see that this is just now is what? It's 15 kilo ohm kan? It's 15K. Okay, so because it's the inverting amplifier, and you know that the gain is R2 minus R2 over the resistance here, so 15 over 2.5, you get minus 6, right? Okay, so now that you know the gain is minus 6, okay, so we know that V out over Vs is minus 6, right? And now you are supposed to calculate what is V out. What is V out? If you are given the V in or Vs is 45 millivolt equivalent to minus 6. So just multiply to get your V out. So V out will be equivalent to minus 270 millivolt, which is equivalent to minus 0.27. So that's how I get the answer here. Okay.